So in an earlier video, we took a look at the theoretical basis for the so-called heat capacity. Here we're going to look at calculations, and first we're going to get one minor issue out of the way. Can CP and CV be related to one another? The constant heat pressure, the heat capacity at constant pressure can be. It is equal to CV plus a factor, and that factor is temperature divided by molar volume, the volume of something when you have just 1 mole of it, multiplied by the coefficient of thermal expansion. And then that whole thing is divided by beta. It ends up that alpha tends to be a pretty small number for a lot of solids. It's on the order of 10 to the minus 5. And if we square it, we get a pretty small correction here. So for many practical purposes, CP is very close to CV. So if you're looking up values, if you're doing temperature calculations over a very small delta T or small delta Q changes in heat, then it's probably not going to make a big difference which one you use. But for serious work, if you're looking at very large differences in temperature or heat and you want very accurate calculations, then you'd probably want to include that correction if you need to go from one to the other. All right, let's take a look at some heat capacities. So if we look up the heat capacity for quartz and galena and water, we will get different kinds of units. And so those heat capacities, let's draw a table that we will put into two columns. One where we have joules per gram per kelvins or centigrade. An interval of Kelvin is the same as an interval of centigrade, so it doesn't change. So, and then we can have joules per mole dot kelvins. And I'll just use kelvins, and again, we can put centigrade here. Well, if we look up values for quartz and galena, quartz is at 44.5 joules per mole per Kelvin. And then galena is at 49.5. Water is usually reported in grams per joules per gram per centigrade, and that comes out to 4.184. How can we compare these? Well, we need to do a couple of conversions. Let's take the case of quartz. Quartz is 44.5. That is joules per mole dot Kelvin. And so if we want to convert that to joules per gram dot Kelvin, we want moles to cancel and grams on the bottom. And the molecular weight of quartz is 60.08 grams per mole. So that means we have 60.08 grams per 1 mole. This allows moles to cancel. We take 44.5 and divide it by 60.8. And when we do that division, we get about 0.741 or 7406 if we take it to 4 decimals. Play the same game with galena, which has a molecular weight of about 239.265 grams per mole, and we will get a value of 0.207. So take a look at this. Oh, and let's do the final calculation for water. Water on a molar basis would be 134.95. So let's take a look at this column here. The heat capacity of water is much, much greater than it is for either quartz or galena. Let's use this. We'll erase the chalkboard to do some simple calculations. Now, in that earlier video on the theoretical basis of heat capacity, we said that Q heat is equal to Cp times delta T. Well, more or less, we're actually missing a value. We have to look at the amount of stuff, and it could be N for number of moles, or it could be, let's say, M for mass. And we can use either the joules per gram dot Kelvin for this guy here, or we can use the joules per mole dot Kelvin for this guy up here. Since we went to the trouble of converting everything to a mass basis for quartz and galena, let's just use that. And so we'll calculate how much heat we need to get a delta T of 80 degrees centigrade, or an increase in temperature of 80 kelvins. And that's not completely arbitrary, as you'll see in a moment. They'll have a neat little experiment you can do at home to figure out the power of your oven. So that means we're going to use Q is equal to Cp multiplied by the mass times delta T. So we know delta T, this is the delta T that we want. We don't have to set it up that way, but in this case we'll calculate the amount of heat that we need given the heat capacities that we've listed earlier, and then a mass. Let's let all of the masses be equal to 10 grams. Let's say we have 10 grams of quartz, 10 grams of galena, and 10 grams of water. How much heat will it take to increase the temperature of any of these fellows? About 80 degrees, or precisely 80 degrees centigrade. Well, we'll go ahead and do the calculations. So for the case of quartz, the amount of heat that we would need, based on the numbers we gave last time, would be 0.7406. I think I rounded it off earlier as 741. That would be the heat capacity. The mass is 10 grams. And then the delta T would be 80 degrees centigrade, or 80 Kelvin. So this is Q is equal to Cp times N times delta T. And that comes out to, if I've done this correctly, 592.48 joules. So that's how much energy we would need to add to quartz to be able to increase it from, let's say, 20 degrees centigrade to 100 degrees centigrade, just to take an arbitrary interval. This heat capacity should be roughly independent of the temperature interval. Actually, it is not. If we have very, very large temperature intervals where we want to do this calculation, we'd have to integrate this over temperature. We'd have a range of values. But we're just going to treat it as constant. If we play the same game for galena, we would get a value of 165.6 joules. That would be the total amount of energy. Plugging in the same values, well, not the same values. This would be the same, that would be the same, with the same amount, the same temperature interval, but we'd have a smaller heat capacity, and so because we have a smaller heat capacity, there's a smaller amount of heat needed, much smaller. We only have to add 165 joules to galena. So this is the galena example, compared to nearly 600 joules that we would have to add to quartz. What about water? So for water, we'll work this out completely again. So we would have Q is equal to 4.184, that's the heat capacity, multiplied by the mass, 10 grams, and the delta T that we are interested in is 80 degrees, and that comes out to 3,347.2 joules. So much more heat is required to heat up water than it does either galena or quartz. So water has a very, very high heat capacity. That means we have to put in a lot of energy to make the system go. So I'll just end here with a suggestion. If you want to have a lot of fun, you should do this. A cup of water is equal to 236.59 grams. So you can figure out the amount of heat that it takes to boil water by doing this. You can take a pot. So here's a pot with a handle, and you could put it on the stove and add a flame. Let's say you add 5 cups of water. So that 5 cups of water would have, if I've done this correctly, about 1,182.95 grams in terms of mass. So 1182.95 grams of water. What you can do is figure out how long, figure out the amount of time, measure the time that it would take to bring that water up to boil. So if it starts out at room temperature, about 20 degrees centigrade, and if it boils at 100 degrees centigrade, then it's the same kind of setup we've had so far. The amount of heat would be the heat capacity, 4.184 joules per gram per degrees centigrade multiplied by the number of grams. So if we have 5 cups, and it doesn't have to be 5 cups, we would have 1182.95 grams, so that's the heat capacity times the mass in grams, and then the delta T would be 80. And so you can calculate how many joules you would need, and then you should also measure the amount of time. How long does it take to go from 20 degrees to 80 degrees centigrade? Let's assume the water starts here. You could do a more precise calculation by measuring, excuse me, this should be 100 degrees C for boiling. That'll give us the 80 degree, that'll be the delta T. The delta T would be 100 minus 20. So that equals 80. So if you look at the amount of time, you would have joules, the amount of energy here that you would calculate, and then you could have time in seconds, and if you did that, then you would have power in watts, and so you can now figure out the power for each of the burners on your stove. So let's say you have a gas or an electric stove, it doesn't matter. So let's say you have 4 burners, like a typical stove. Try measuring each of those burners and see if any of them have a difference in power, and you can calculate that power in watts, which is as the standard units of joules per second, by doing this calculation and dividing by the amount of time in seconds that it takes to boil water. And of course, if you want to do it very precisely, instead of just guessing at kind of a room temperature starting point for the water, measure the initial temperature.